Today in this video, we'll discuss about the effect of dielectric on the capacitance. In the last video, we have discussed about the capacitance of a parallel plate capacitor, and the vacuum was in between the two plates. Here we'll put in dielectric in between the parallel plate capacitor, and we'll see what is the effect of dielectric. Now, dielectric are basically insulator and the basically polar molecules. So if we'll keep the dielectric in between the parallel plate capacitor, let's say it's completely filled in between the two plates, and this is dielectric. So it will have molecules, and as they are polar molecules, so they will be aligned with the electric field by the capacitor plates. So the plates, let's say left side plate will be positively charged, the right side plate will be negatively charged, minus Q. This is, let's say, plus Q. So due to these charged plates, there will be electric field, and we have calculated the electric field in the previous video. Here the dielectric will have the molecules, and they will be polarized. They will be aligned along the direction of the electric field in between the capacitor. So the molecules of this dielectric, the negative charge will be towards the positive plate. All the negative charges of the molecules will be accumulated one side and towards the positive plate. It should be, because these are negative part of the molecule, so they will be attracted towards the positive side, and positive side will be repelled, so they will be away from the your positive plate. Now similarly, the right side, there will be so many molecules, but I have drawn few molecules, and all the molecules will be mostly oriented in this way. And the similar fashion, the positive side will be attracted towards the your negative plate. So all the positive charges or positive part of the molecules, they will be accumulated at one at the right side surface, which is near the negative part of the plate, negative side of the plate. Now opposite side will be minus. So what will happen, basically this positive negative, they will cancelled out, and the surface which is near the negative plate will generate a positive phase, you can say, and one negative phase will be created, or negative surface will be created at near the positive plate of the capacitor, right? And these are called the induced charge. These are the induced, you can say, we'll write that the sigma p will represent sigma p, that is the polarized your charge density, right? So left side is minus sigma p, and right side is creating a charge density that is plus sigma p, and the negative plate is minus sigma, the positive plate is plus sigma, a charge density of the positive plate. Now if you remember in the last video, the electric field we have written, that is sigma by epsilon naught. In between the plates, it is sigma by epsilon naught. So here the sigma will be modified. Sigma is the charge density of the either side of the plate. Now here the charge density will be modified. The charge density will be modified because net charge density, we can say, here due to the parallel plate capacitor, plate of the capacitor, it is having plus sigma, and due to the induced charge, due to the polar molecules, this is creating a minus sigma p. So net charge density near the left side. So at the left side, you can see the net charge density, it is sigma minus sigma p. And in the right side, it is minus sigma minus sigma p. Because this is plus sigma p, so we can write simply it is plus sigma p minus sigma, the net charge density, or I can take one common, right? This is plus, so I can take common minus one, so this will become sigma minus sigma p. So why I am writing in this way? Because to make the left side and right side in the same form, sigma minus sigma p. So we can say the left side having net charge density plus sigma minus sigma p, and the right side will have the charge density minus sigma by sigma p. So the electric field which was we have written, or we have calculated for the parallel plate capacitor vacuum inside, only sigma by epsilon naught. So here will the electric field will be sigma minus sigma p by epsilon naught. This is the electric field in between two plates. This is the electric field in between two plates. So now we will write this sigma minus sigma p in terms of a new constant. We'll introduce a new proportionality constant, that sigma is equal to k times sigma minus sigma p. That means more is the charge on the plate of the capacitor, there will be more induced charge. So sigma minus sigma p, if we subtract, then also it will increase. That means more is the charge on the capacitor, more will be the sigma minus sigma p. The difference between sigma minus sigma p also will be will increase. It will be proportional. So we can multiply a proportionality constant, and this k is called your dielectric constant. This is dielectric constant. And for vacuum, k equal to 1, and it is more than 1 for other dielectrics. So k is not non-negative, so we can write that sigma minus sigma p equal to sigma by k, we can write, right? So a sigma will be greater than sigma p, so it will have a positive number, so that's why sigma is also a positive. So k should be your greater than 1, so that 1, either 1 or greater than 1, so that it should be greater than 1, so that you will multiply with a positive number and you will get a sigma. If means a more than 1, right? If it will be less than 1, then again the sigma minus sigma p, it will contradict, so it should be greater than 1. So now if we'll replace this sigma minus sigma p here in this equation, let's say 1, then so from 1 we can write that E equal to sigma by k epsilon naught. Now the relationship between potential difference and electric field, we know that your V equal to ED, and E is here sigma by k epsilon naught D, right? And our interest is to calculate the capacitance, how the capacitance has modified from the previous case. This is our aim. So in previous case, our capacitance was C equal to, for vacuum, it was, let's say C0 is equal to epsilon 0 A by dd, is the small d is the distance between the two plates of the capacitor. Let's say this is the D, right? Now we'll see that we have kept a dielectric in between the plates. Now we'll see that whether the capacitance is increasing or decreasing. So your C will be, capacitance C is Q by V. So V we got here from, let's say, 2. So from 2 we can write your C is equal to Q by V is sigma by K, or you can say sigma D by epsilon K, or epsilon K will go up. I can write in this way. And what is sigma? Sigma is the density. So you can write Q epsilon naught K. Sigma is Q by A. So A will go up again to the numerator. So D, Q cancelled out. So is C is your epsilon naught Ka by D. So the capacitance of a parallel plate capacitor, when dielectric is there in between the plates, then your capacitance is modified epsilon naught Ka by D. So if we'll see that basically it is your C is epsilon naught A by D is C0. So K into C0. C0 is the capacitance when vacuum is there in between two plates, there is no dielectric. So only if we'll multiply dielectric constant with your capacitance, that is vacuum in between two parallel plates. So just you will multiply K, then you will get the capacitance for the your when the dielectric is there in between the plates, right? So C equal to KC0, or another equation also sometimes important, the K equal to your C by C0. C by C0. Also, this epsilon K is also represent, we represent this one as permittivity of that medium, the dielectric, right? We have kept the dielectric in free space. Your permittivity is epsilon 0. So epsilon 0 into K is your epsilon, that is the permittivity of the medium, or you can say K is equal to epsilon by epsilon naught. That is epsilon is the permittivity of medium, right? Epsilon 0 is the permittivity in free space. Here permittivity in the medium, like let's say the dielectric, any dielectric, that its permittivity will not be epsilon 0, right? So it's permittivity of the medium. So this is your the capacitance which is modified when a dielectric is there, and it is modified K times. So it is K times the capacitance increases K times, then nothing is there, or vacuum is there in between the plates, right? So in the next section we'll discuss, next video we'll discuss that the capacitors in series, capacitors in parallel, and also we'll solve a numerical based upon this capacitors in the next next video. So thank you. In the next video we'll discuss parallel series and combination of capacitors, that is series combination and parallel combination. Thank you.